Well, very good. Yeah, so I'm going to talk a little bit about some work that we're doing at Purdue. I know Jane and I are working on a tool, what we call the Drainage Water Recycling Evaluation Tool. And what this tool is meant to do is really start to give us some of those initial estimates of what this practice of drainage water recycling might be capable of, right? And really this question is of interest as we look across the Midwestern landscape where we have variable conditions. And so I'm going to talk about some of the results that we're seeing from that analysis now. And so we've heard before from Katie, right? So we have a whole toolbox of practices and power drain landscapes. You know, what are these effectiveness? What are these reduction efficiencies of these practices? How does that vary, right? And how does that translate in terms of the potential to put these on the ground? You know, these are the questions that we're really wanting to get at with designing these drainage water recycling systems, right? How large does this on-farm water storage size of the system need to be? How will that size requirement vary across the region? So those are really the two primary questions that we're asking here. And the talk today is focusing primarily on the water quality aspect. So I'm not going to get into too much of the irrigation side. The two are linked quite a bit. We'll see a little bit. So to do this, kind of the basis of this tool that we started to put together is we want to link that soil-water balance, right, that we think of in the field to a pond water balance where that drainage water will be stored. So obviously some key terms here are that drainage, that D term, right, that link the field to the pond. This analysis is assuming only subsurface drainage, so I'm not necessarily thinking about the surface runoff. But then the other key term here, right, is that irrigation term. So withdrawal from the pond back up onto the field, and that kind of completes this continuous loop of the system. So just to walk through those really quickly, starting with the pond water balance. Here we see the basic water balance that we're running for the pond. So the primary inflows to that pond are natural precipitation onto it or into it, and the precipitation or the drain flow flowing through the tile system, right? And so both of these in this case were field measured. Now losses from that system are going to be surface evaporation, seepage losses, irrigation withdrawals. I know thanks to Dr. Laura Bowling and her student Charlotte Lee at Purdue, they have the gridded regional VIC model. So we use that as a source of the surface evaporation estimates. And for this study, we just held seepage constant at 0.99 millimeters. And so this is a number that comes from some of the NRCS engineering guidance. Now that soil water balance in the field. So again, I'm sure most of us are familiar, at least in concept, to this water balance or soil moisture balance. Here, the primary additions to soil moisture that we have being tracked are that precipitation again, irrigation, which I'll explain in just a second, and one recent addition that we've added into it is this capillary rise term, right, which isn't necessarily the easiest thing to measure. We are estimating, and I underscore that quite a bit. We're estimating, but we do have field measured water table, and so we've used that field measured data set in the soil utility and drain mod to try to get some estimates of how much capillary rise is occurring and actually being used in that crop ET. And then outlets to that soil water balance, obviously are the runoff, which occurs on the surface, and then crop ET, which is taking that water up. And so the irrigation is coming from this crop ET estimate and soil water balance. So we're using the FAO guidance, which is fairly standard, right, in terms of estimating the crop water use. If that water isn't present in that soil water balance as it goes up and down, that's when we call for that irrigation from the pond. And so this is how we're kind of closing that loop with those irrigation estimates. And so putting this all together, what are these scenarios that we see, right? So as we add water to the system, it goes into the pond. So if the capacity in that pond is greater than the incoming flow, we call that captured. captured and stored drainage. So this is where that water quality benefit is going to occur, right? Now, if capacity isn't there in the storage, if flow exceeds it, we're going to let that flow go on downstream. So that's a downstream discharge. We cannot hold it. We do not have the capacity. From the irrigation side, again, if crop ET, if that crop wants water and it's not present in the soil water or that soil profile, we're going to pull it. We're going to pull it from the pond to meet our target application. In this case, we set that target application to 1 inch. And so we just used a flat rate for this analysis. Now, if that volume isn't there in the pond, we do count that as deficit, and we let that crop be stressed. And so these are the scenarios, right, that we're evaluating, and we're trying to play that what-if scenario to say, okay, is my pond big enough? If it's not, what effect is that having on the crop? What effect is it having on how much I can capture of that drainage? So putting this into application. So we used a field measured data set from Davis Purdue Ag Center in East Central Indiana. I want to thank, Dr. Bowling again and Jane Frankenberger, obviously, for this data. And then also the Southeast Research Farm in Iowa, which Matt Helmers provided some of the data for this. And so we have 10 years of daily data here for drain flow, water table, climate, and nitrate that we used as input into the model. And we looked at various storage sizes. So a storage size which represents 2% of the field area, 4, 6, 8, and 10%. And here our field area is 80 acres. So a 10% storage is 8 acres. At an average depth of 3.05 meters, 10 feet. And there's the field area. So and I'm going to set this up a little bit because I'm going to go through it, but it really is a tale of two sites. And so when we look at average precipitation, in this case in DPAC, the average rainfall value is a little over 1,000 millimeters per year. About 45% of this is occurring in the growing season. You see the range below. This is the subsurface drainage that we see. And again, these are kind of paired boxes, right? So the black box, what would be on your left, is the annual amount. The red is the growing season amount. So we see a lot of drainage occurring, right, throughout the year, but very little of that is occurring in the growing season. Now, compare this with what we're seeing at Surf, Iowa. Again, we see a similar average rainfall amount, a greater amount occurring in the growing season, which is going to be an important point as we move through the next couple slides. And as we look at the annual drainage versus growing season drainage, again, a much greater component of that drainage throughout the year is occurring during those growing season months. And so these are key differences to keep in mind, right? So the timing of that precipitation and subsurface drainage, and also, this is the first time I'm bringing it up, but the soil water storage. There's about 100 millimeters more storage, what we're estimating at Surf than at DPAC. So let's get into some of the results. And here we're going to look at so that portion of the flow that is held within the pond or the on-farm water storage here. And so just to illustrate this difference in timing, so 2008 was roughly an average year in terms of rainfall for DPAC. I apologize for this. I didn't have time to quite polish it up. So the light gray in the back is the background drain flow, right? So it's going up and down throughout the year. We see a lot of it occurring over here starting in January all the way through February, March, April, and then it starts to taper down as we get further into the growing season. Where we have colors is where it's being captured by certain sizes of storage. So what I want you to take away is that we're capturing in the winter. We have bypass or downstream discharge, right, starting in early spring, going through that early growing season. Now this is Surf. And so we see a much different pattern, right? And so I qualify this. This is 2014. So in Iowa, we just came out of the drought of 2012 and a fairly dry year in 2013. We have essentially an empty pond or empty storage in this case. But when we don't see a whole lot of winter drainage or even early spring drainage in this case. But as that drainage starts to pick up, we see virtually complete capture, right, of that drainage. And what's really interesting is that we see, so this dark blue color here is the smallest storage size, 2%. So it captures this initial flush, gets drawn down when we apply irrigation, and then it's capturing again. So you get these repeated captures. And this is the significance of having that drain flow during the growing season, right? So we capture that drain flow during the growing season. It's a pretty short turnaround to when we're using it. Versus at Indiana, we see a much longer storage period that we have to cover. And so this influences the effectiveness, what we'll see the effectiveness of the practice. And so these are all 10 years. And so the average is the yellow dot. This is maximum, minimum, so a stock chart, essentially, GPAC on the left, surf on the right. And so just to walk through this, at 2%, you see slightly larger amounts at surf. This gap is starting to decrease as we increase in size. And by the time we get to the largest sizes, it's essentially the same amount of capture on an annual scale. And so, again, what is happening here is we see some lower lows. And so think back to the soil water storage capabilities at surf. We can store a lot. There are some years where we get enough rain where we don't need to irrigate. We don't need to pull water from the pond. And if the pond is full, we aren't going to capture. And so that's what we're seeing here, is that there are times where we have a full pond and it remains pretty much full because we have enough rain. Where you see some of these increases, the higher amounts, both in terms of the means and the maximums, again, are kind of that timing nuance that we just talked about, right, where we have the larger portion of the flow occurring in the growing season, so we can apply it quickly, turn around, and capture more, and so that results in greater percent of capture at the site. So what does that look like in terms of load? And here we're talking about, again, that nitrogen moving down through the tile flow, being dropped into the storage. We see a similar pattern, but here we see some differences growing even more from these sites. Again, the same type of chart layout, surfs on the right. We see a much greater range during some of these years, and these are repeat captures, right? And so you're getting nitrogen loads moving through the system, and you're capturing multiple times throughout the year in some of these cases. But essentially by the end of this increase in size, this larger size of 10%, the performance starts to equal out. And so larger sizes eventually catch up and trump that. They're able to capture early in the season, hold them for long periods. So, and finally, the annual nitrate percent reduction still follows this similar pattern. And so here, what I want to point out is, again, we have some of these nutrient reduction targets in place, right? That 40% mark that we might be looking to hit. We can start to look at what sizes start to hit that 40% mark. So here at 6%, we hit it at the DPAC site. Here at 4%, we hit it at the surf site. So that target in terms of size is going to change as we move across the region. And that's essentially what I'm showing here as well, so I apologize. But we see that 40% roughly mark, and that refers back to the 6% storage at DPAC and the 4% at surf. So moving forward, we certainly still have to do some sensitivity analysis on this tool, this model, so to speak, just to see what some of these input changes, how big of an influence they're going to be, right? So you think about things like capillary rise. That's a fairly rough estimate, hard to measure. What changes are those going to have? And we have the blessing of being part of the Transforming Drainage Project, being able to work with a wide group of people a large number of sites, a lot of data, so we can certainly look to scale this across some additional sites. And then we will have this, as the name suggests, as a tool, and so we are working to make this available online here in the coming months. So with that, yeah, big questions.
Very good. Question for Ben?